the state bifurcation of this Telangana and Andhra. So central government has sanctioned the new NIT and the IITs to the Andhra Pradesh state. So in that actually we got here in Thadepalli Gudam. It's a West Godavari district actually.
Where is IIT? In Tirupati, right?
IIT in Tirupati, sir.
Tirupati.
So we are close to Vijayawada, like
You are close to Vijayawada.
Yes, sir. 100 kilometers actually.
And Visakhapatnam is how far?
250 kilometers.
250.
Yeah, but we are on the highway of Chennai to this Kolkata on highway, sir, actually.
Oh, okay.
So connectivity wise, it's good actually. So nearest airport is Vijayawada International Airport.
Oh, okay. Very good.
Yeah.
So
yes.
Settled there now. You are from the same place?
Yes, sir. Yes, I am from Nellore, close to
Tirupati.
Yeah. Sandeep, can you hear me? Dr. M. Sandeep?
Yes, sir. Yes, sir. Yes, sir.
Yeah, you can switch on your video, please, for a few minutes.
Good evening, sir.
Hi, Sandeep. How are you?
I'm good, sir. I'm good. How are you, sir?
I'm all right. So I was telling him that I keep confusing between your name and his name.
Yes. Yeah, lot of people confuse actually. Yeah, it's okay. Actually, we both are.
But I have your number. That's why I have only one Sandeep number. That's why message goes to you all the time.
Yes, sir. So
I know you gave me your number when I visited IIT Delhi. Still, so I have that number since then.
Yes, sir. Yeah, I met you in Singapore as well.
Yeah, Singapore. Yeah, 2 years ago.
Yes, sir.
So this video is okay, right?
Yes, sir. It's fine, sir.
Very good. Because that is better. Sometimes this Ned Mohan told me to do like that.
Yes, sir. We had his session in the last year, sir, actually.
Oh, okay. He told me, then you don't have to worry about all those audio, video connections and goes. Sometimes
yes.
Is not good and all those things.
Yes.
So, Sandeep, which company you work for in Singapore? I think he got.
Actually, I was previously our research institute, like Experimental Power Grid Center, EPGC was under A-Star. Now we merged with ARIAN, Energy Research Institute at NTU. So now we are part of NTU.
Oh, okay. You work with Subodh.
Yeah, Prof. Subodh. Yes. Yeah. Previously we were under A-Star. A-Star was like
yeah, I know.
Agency, yeah, a Singapore government agency.
So now the EPGC is part of NTU.
Yes, part of ARIAN.
Yeah, that is which is part of NTU anyway.
Yes, sir. But our work location, everything, and the business and all is same. Like our management, like high level management changed to NTU.
Oh, okay.
So now I am employee of NTU, like staff of NTU.
But you sit there in NTU or in the EPGC?
EPGC.
Okay.
Yeah.
All right. I think,
so currently we are taking up some microgrid related projects, and we are working on wide band gap devices, like gallium nitride based high power density converters. related to smart grid, renewable energy integration, solar PV intermittency mitigation, all those energy storage system. These are our work capabilities or the work profile that we take.
Yeah. Very good.
Okay. Sir, shall we start
Yeah.
now?
Yeah.
Okay. Yeah. Very good evening to all the participants to the fellow talk program today, this evening. And very good morning to sir, actually, for you, Dr.
Thank you.
Kaushik Rajashekara, IEEE fellow. And sir, actually, ours is a new section, IEEE Vizag based section, started in 2020. And we have the couple of technical chapters under this section. And ours is IEEE Power Electronics, Industry Applications, and Power and Energy Joint Society chapter. Last year we conducted very good number of programs, more than 30 programs we conducted in short span of 3 months, and we are continuing the doing the very good quality programs in 2021 also. So as part of that, actually we have initiated the fellow talk in 2021. So we would like to do this fellow talk every month, at least one talk by IEEE fellow. So we are very much honored today, sir, actually, to have your first talk by you, actually. And we were very happy to get your slot. And thank you very much for accepting our invitation and joining for today, sir. Thank you.
Thank you.
Now, and I request our section chair, Dr. Lakshmi Narayana, Vizag Bay section, to speak few words on this occasion.
Professor Rajashekara, Professor Sandhi, and another Professor M. Sandhi, and other dignitaries on the board. In fact, really, it is a wonderful morning to them and evening to us to see Professor Rajashekara with us today. In fact, I think you already briefed about our section, our very, very new section, sir. And we are a subsection from 2011. We conducted several international conferences also in this area. We conducted several events, and this year we are a small section. In fact, we have bagged the highest first place in the entire region 10 for the incentive for the best performance in 2020. In fact, we have done that from the September to December, sir. Our active work started only from September. In the 4 months, we could do quite a lot of number of programs with the help of the many of the volunteers in and around in our section. We have done well, in fact. This year also, we expect similar thing, and with your help, certainly we will shine better. We request you to bless us on this occasion. And next, we are conducting a conference in July, August, sir. I request you to kindly propagate the links to your scholars, your people, etc. to them, so that they can send some of their publications to us. Our acceptance ratio is around 20%, sir. We don't accept more than 20%. Plagiarism content also around 20% only. We don't send review even the paper has more than 20% plagiarism. We reject at desk only. Therefore, our quality of papers are very good. We accepted last year 25 papers out of 206 papers. Good evening, Professor S.S. Murthy also. He is online now. And this is a kind of a quality we are trying to build up. My team is very good, sir. I need not tell 100 times that my team is good, etc. I need that your support and kindly extend our links to your researchers to send some papers. In case they cannot come to India, also we'll extend through WebEx or any other media to present, so that our conference will have much visibility to you. And one more thing I would like to submit to you, sir. In fact, my son studied in your college only, in your department. He did a MS in
Houston?
Yes, University of Houston. His name is Sadasivani Sudarshan. Sudarshan Sadar. I'm the father of Sadasivani Sudarshan, who studied in your department only. He is now doing a PhD in University of Buffalo. He is doing PhD in University of Buffalo. In fact, I referred after knowing your name about to my son. He said that sir is a very senior professor. He was mentioning to me on that occasion. That was the background what I could say. In fact, very welcome to sir. Kindly bless us and bless our team, sir. Thank you very much.
Thank you very much. I see that my good friend Professor Murthy is also here. Nice to see.
Yeah.
After a long time.
Yes.
I'm glad you were able to join.
Yes. You can listen.
Yeah,
Okay.
I can hear.
You can listen to me.
Yeah, sure.
Yes, we can.
Yeah, very nice talking to you.
Yes. Long time. You see, when Sandeep told that you are talking, then I cannot miss the talk.
Oh, thank you.
I don't want to miss you.
Thank you. So we are all working from home only. Anyway, at home, everything.
Yes.
It's a very bad situation here.
I think now America seems to be worse than India.
That's correct. America is worse than India.
I hope the new president will make some change.
Yeah, it will take some time. It will take some time.
Okay.
Okay.
That's right.
Okay. Thanks for joining, sir. Professor S.S. Murthy, sir.
Yeah. Anyway, it's my pleasure.
Yeah, thanks. Now I request Mr. Chandrasekhar to introduce the speaker to the participants, please. Yes.
Sir, Kaushik Rajashekara, fellow IEEE, received the PhD degree in electrical engineering from the Indian Institute of Science, Bangalore in 1980. In 1990, he joined the Delhi Motor Station in India.
I think he is breaking his voice.
Yeah. Your voice is breaking.
Hello.
I think there is a microphone problem.
I think Sandeep, you can introduce him so that.
Yes, sir, I can do that.
Yeah.
Thank you. Yeah. So it's a great privilege to me to introduce Dr. Kaushik Rajashekara to the audience, and he has received the PhD degree in the electrical engineering from Indian Institute of Science, Bangalore in India in 1984. And in 1989, he joined Delphi Division of General Motors Corporation, USA, as a staff project engineer. In Delphi and General Motors, he has held various lead technical and managerial positions, and he was also as a technical fellow and chief scientist for developing the electrical machines control power electronic systems for electric, hybrid, and fuel cell vehicle systems. In 2006, he joined Rolls-Royce Corporation as a chief technologist for more electric architectures and power conversion and power control for aero and marine, defense, and energy applications. In 2012, he joined as a distinguished professor of engineering with the University of Texas, Dallas, USA. And after that, since September 2016, he has been a distinguished professor of engineering in University of Houston, USA. And he has authored and co-authored more than 250 papers in international journals and conference, and he has 35 and then 35 US and 15 foreign patents, and has written a book also, and he has given more than 250 invited presentations and talks at various forums like international conference and universities. And his research interest includes power energy conversions, transportation electrification, and renewable energy and microgrid systems. Professor Rajashekara is a distinguished alumni of IISc Bangalore and fellow of SAE International. He was elected as a member of National Academy of Engineering in 2012 for the contributions of electrical power conversion systems in transportation. So he was also elected as a fellow of National Academy of Inventors in 2015 Also fellow of Indian National Academy of Engineering in 2013. Also, he was also contributed as a IEEE Industrial Application Society Distinguished Lecturer as well as Vehicular Technology Society Distinguished Lecturer. He was the recipient of the various number of awards, including IEEE Richard Hodel Award, IEEE Industrial Application Outstanding Achievement Award, IEEE IAS Skillment Award, and IEEE PELS Vehicle Transportation System Award. And this year, very recently, I mean, we all get to know that. So he is received in 2021 IEEE Medal for Environmental and Safety Technologies Award, actually, from the IEEE. And also that's how he has contributed to various development technologies in power and energy sector. So thank you very much, sir, for being here with us this evening. Thank you so much.
Thank you, Sandeep. Thank you for the introduction and
Yeah.
thank you for asking me to give this presentation here. I'm very happy to give this presentation. This newly formed institute 5 years ago, right? About less
Yes,
than 5 years
yeah.
old, this university.
And then our section is just, not even less than 1 year, sir, actually.
Okay.
IEEE section.
Thank you.
Yeah. Thanks. Yeah. So can I share the content,
Yeah.
sir?
Yeah.
Yeah.
I think audio is missing. And also, can you put it on the full screen?
Sorry, sir.
Audio is missing and also you're not on the full screen. Click on the
Okay.
bottom of the arrow that makes it full screen. Yeah, that one. And then audio is not there. What happened to the audio?
I think you'll have to share the audio, system audio.
Sir, what about our voice, please?
No. What happened to that? I think when you tested, it was working all right, right?
Yes, sir. Yes, sir.
So I don't know what your.
We can hear.
Oh, you can hear.
Okay.
Oh, we can. I cannot hear some more. Yeah.
Is it so, sir?
Maybe.
What about others, please?
We cannot hear the video, the audio from the video that you are doing, but we can hear your voice and we can hear the
Okay.
professor's voice also.
Okay.
Okay.
Okay. Let me.
Sir, please check the settings while sharing the screen, sir. Maybe I think while presenting the screen, you may find the option that share audio. I think.
Yeah, 1 minute. We're trying to.
Not come in full screen.
Yes, sir. I'll make full screen. This is full screen, actually.
But audio means we can hear Rajashekar.
But no, audio of this videos or this recording, this is a problem. Okay. What about now, sir? Would you,
We can hear you, but we can't hear the audio from the clip.
yeah,
If you're running the app, try seeing the share settings.
Okay, I can do one thing. I can share. I can do it from here. You want me to do it?
yes, sir. Yes, sir.
I have to first share. Let me first. You need to give me a share, right? Share. Okay.
Yes, sir.
And I will do it. And now, one second. Oh, 1 second. Can you hear this video?
Yes, sir. We hear you, sir.
You can hear my presentation?
No, sir. We may not see
I
your
have to share a screen. Say.
Yes, sir. Now we are getting, sir.
Okay, I will do it from the beginning.
Yes, sir. I'm sorry for inconvenience, sir.
You can hear, right?
Yes, sir. It's perfect now. Yeah.
Oh, okay. 1 second. Let me put it on the full screen and then I will start talking. Okay.
Yes, sir. Thank you, sir.
Okay.
Sir, no, sir. We may not able to hear audio, sir.
Yeah. Sir, it's the same problem again.
Oh, you cannot hear?
Yes, sir. Yeah. We cannot.
You can hear or no?
No, sir. No, sir.
Oh, I don't know. That is from your side.
Yes, sir. It's my side. And from the recording, we are not able to hear the audio.
No. Now I am doing it. My recording, my voice you cannot hear.
And
We can hear your voice.
But not my presentation.
Presentation, no, sir.
So sorry to interrupt. While sharing in the more options, there might be an option to switch audio. So in the switch audio, we'll have something like you might have the option maybe.
No. This is the problem in the WebEx, I think.
Yes, sir. Actually, here I don't find such kind of option to sharing separately the audio content. And
So, okay, I think maybe I will start giving a presentation from the slides.
yeah,
This was the recorded lecture, is it?
Yeah. So you cannot hear anything from the recording at the background?
no, sir, we are not able to hear, sir.
Oh, you're not able to hear anything.
Yes, sir.
Yeah. Then there is no, I will stop this video then. Let
Yes.
me go back to, where was that? Where is my, sorry, where is, yeah, start, sharing. So, okay, so it doesn't seem to work. Let me do one thing. Let me screen share. But you were able to see the video, right? Not the audio.
Yes, sir. We are able to see video. I mean, not audio.
Can you see my?
Yeah, this presentation slides we are able to see now.
No, we are seeing the slides.
Yeah, slides
But-
now itself. Yeah.
So can you hear me now?
Yes, sir. Yes, sir.
Okay, I think we are already 8:25 now. So I will try to go a little bit faster then. I will give this presentation on my own now.
Yes. Thank you, sir.
I thought we can avoid this audio video problems if I send it recorded so that it is more easier, but the other way seems to. So, yeah, thank you for inviting to give me this presentation. So I will be talking on propulsion systems and power electronics for electric, hybrid, and fuel cell vehicles. So the petroleum consumption has been increasing for a long time, but except this year, actually the petroleum consumption has come down this year because of, this year means in 2020 because of the COVID. But the emissions are considerably still higher. For example, global emissions in 2019 were 34 gigatons. And out of that, United States 4.9 gigatons, and China double that, 9.8, and India half of US, about 2.9 gigatons of carbon dioxide. Can you hear me?
Yes.
Okay. So the transportation, this is for the US. US transportation has 28% of the emissions are from the transportation itself. And rest of the industries are lower. Even the aircraft produces 9% of the emissions, that is in the US. Globally, the aircraft produces about 3% of the emissions. So we need to reduce the emissions from the transportation sector. That is the main idea. So what do we do? So the electric vehicles are the best method for reducing the emissions. So just I want to give you, because this topic is propulsion and power electronics for electric and hybrid vehicles. So I want to focus on the power electronics and propulsion aspects for the electric vehicles. So if you look at the, it's a vehicle. So the propulsion is provided by the electric motor. So there is no internal combustion engine. And where does the power come to the motor? The power comes from the battery. But battery is DC and motors are all AC. Right now, all the automotive manufacturers, they use AC motors, mostly permanent magnet motors. All of them use interior permanent magnet motors. So that's why we convert battery voltage to AC. So we need an inverter. And then the inverter converts it to variable frequency, variable voltage. So you can control the torque and speed of the motor. So that will in turn, we can control the speed of the motor and the power or the speed at which the vehicle goes and what level and all those things. The entire vehicle can be controlled by this motor. So this is power electronics inverter, and you see that there is a converter here. This converter is an interface between the battery and the inverter. So the battery voltage can be at a lower level, but the inverter needs a higher voltage. For example, inverter may run at 700 volts, battery may be only 200 volts. So you need a boost converter. So generally we use a boost converter, but it is not necessary that you have to use this converter in all the vehicles. For example, Tesla or General Motor vehicles, they don't have this one. And also the vehicle from Prius, most of you are familiar with Prius. Prius is a converter, like this is a boost converter. So you can see that red thing on my screen. You can see this, right?
Yes, sir.
Oh, okay. Just want to make sure that. And then there is another converter, another DC-DC converter, this one at the bottom. The function of that DC-DC converter is to bring down the battery voltage of 300 to 400 volts to 14 volts level, because there is a 12 volts battery here at this point. The 12 volts battery has to be charged, and it provides the power for all the accessories. For example, those who are driving the vehicle, you see that there is always 12 volts battery in your car. So that 12 volts battery provides the power for all the accessories such as lighting or like door openings or power steering, electric power steering, and that type of thing. Okay. And there is another power electronic unit, that is the charger. This is the onboard charger. It is from say about 3 to 6 kilowatts. So that is always inside the vehicle. So whenever you want to charge the vehicle, there is an outlet. You connect the outlet or the cable to the outlet, and you can charge the batteries. So the power electronics components here are the inverter, this converter, and this charger. Okay. Of course, they all have a control system. So this converter, I was talking to the DC-DC converter. That is a 14 volts, which converts from high voltage to low voltage, say 200 to 400 volts to 400 volts. So this converter can be an isolated, or it doesn't have to be isolated. Mostly it is an isolated converter. So that is why we use a transformer. There are various ways of converting the high voltage DC to low voltage DC. Okay. So generally we have a high frequency inverter, then it goes to the primary of a transformer, then you rectify it and get 14 volts. So it is a unidirectional converter, one direction. But this converter which is at the top, there is a bidirectional because the battery also has to be charged. But this one is only one direction. Okay. And the converter between the battery and the inverter, the bigger one. So that converter is also called the energy management converter or a boost DC-DC converter. Even though it does buck boost converter because it is a bidirectional, generally Toyota in their diagrams, if you see, they call it a boost converter. So the battery voltage can be around 250 to 400 volts, but the DC link can be 650 volts. That is in Toyota Prius. So what is the advantage of having this converter? The first thing, it makes the battery voltage compatible with the inverter voltage. Because if you have 250 volts here and if you need 650 volts also, you need a boost converter. Okay. And also it maintains the voltage. The battery voltage can vary over a wide range. By controlling the operation of this boost converter, you can maintain the voltage at 650 volts. Okay. So regarding the inverter, this is the inverter. Generally, it is a 6 devices, or three-phase bridge inverter, and it's controlled with vector control. We will not go into details of those things. So basically for controlling the driving torque, braking torque, and motion control. So it gets the signal from the acceleration pedal and the braking pedal and also vehicle speed signal. Many times the driver is the one who determines the speed, right? So these are all done by the controller. In addition, there is a controller for DC-DC, this DC-DC converter and this DC-DC converter and this charger. They are all separate controllers for that. So first, the electric vehicle, I would say, commercial electric vehicle was GM Impact that was brought out in 1990, and the technology of which led to EV1. But the electric vehicles themselves are very old, more than 100 years old. The first electric vehicle was invented in 1837. So even in the year 1900, there were more electric vehicles sold than the internal combustion engine-based vehicles. The reason is at the time, the gasoline vehicles were more expensive than the electric vehicles. But gradually, the gasoline vehicles cost came down, and also the starting of the engine, the self-starting was invented. Then it became very convenient, and by 1920s, actually all the electric vehicles disappeared. Till 1990s, when the EV1 was brought out or commercialized. But between 1920 and 1990, there were a lot of demonstration vehicles, but not commercially available vehicles. So this EV Impact, or the technology of which led to EV1, it had two motors in the front wheels, induction motors. Each one was 57 horsepower, and it could go 100 miles per hour. And I happened to work on this vehicle. So we used 288 MOSFETs, means there were two motors, so we used two inverters. Each inverter has 144 MOSFETs. So that means each device has 24 parallel connected MOSFETs. So at that time, there were no IGBT. So the MOSFET was 600 volts, 20 ampere from Axis. That was the company at the time making AXYS. That was a 600 volts, 20 ampere devices. So they would put 24 in parallel. So that's why because there are two inverters, 288 MOSFETs. It was an induction motor based system. Now nobody uses induction motors. They all use permanent magnet motors. And base speed was 6,600 RPM, corresponded to 220 hertz, 4-pole motor. And the battery itself was weighing 395 kilogram. That is a lead acid battery. And total vehicle weight was 1,000 kilograms. And this is the GM EV1. Everything was electric here. Electric air conditioning and electric heaters, heated windshield. Everything was electric here. But this in 1999, General Motors stopped this vehicle because the vehicle was quite expensive. And also the Prius came in 1997, the Toyota Prius hybrid vehicle. So it was giving, there was no range anxiety. The EV1 was giving only 18 miles of range. So that was a big concern, and also it was quite expensive. So basically, in a way, people thought that now the hybrid vehicles have come up. No, that is the end of electric vehicles. But things have changed. Tesla brought this Roadster in 2008. That is a quite expensive vehicle, $100,000. It was costing approximately, but it was a very elegant and very nice car, more like a luxury car. And people who had a lot of money, as a status symbol, they bought those vehicles. And it had a range of 220 miles. That was very good. And there was no lithium-ion batteries those days. So that means they were there, but not as a modules for the electric vehicle. So they took that laptop computer batteries, connected 6,831 lithium-ion batteries in series and parallel to make a battery unit for this vehicle. So it went very well. People started liking that vehicle, and of course, many could not buy because of the cost. In 2012, they introduced this Tesla Model S. This became very popular. And also, it had a range of 230 miles with 60 kilowatt hour battery, or 300 miles. That is nearly 500 kilometers of range with 85 kilowatt hour battery. And it still uses the induction motor of 310 kilowatts, 600 Newton meters. But the range anxiety was of less concern in this vehicle. And also, there was a 10 kilowatt capable onboard charger, so the batteries could be charged relatively faster when compared to the 3 kilowatt chargers, which was used in the earlier versions. Okay. So that was a very good vehicle, and it became very popular. So then gradually the other companies also started working on the electric vehicles. Though, for example, Nissan Leaf was available in earlier vehicles, and so there are several electric vehicles also came. So Nissan Leaf had 107 miles of range. Can you hear me? Hello? Can you all hear me? Can you hear me?
Yes, sir.
Oh, okay.
Sir, sir.
Oh, okay. Because just say. So then, so now there are so many types of electric vehicles are available. So every auto manufacturer has an electric vehicle now, and electric vehicles are taking off now, and a lot of people are interested. And yesterday only, General Motors, the world's world's biggest car manufacturer, announced that by 2035 they will not produce any more gasoline-based vehicles. All the vehicles will be electric vehicles. So by 2035. So now I will give you something about, tell you something about the hybrid vehicles. So hybrid vehicles, there are mainly two types of hybrid vehicles: series hybrid vehicle and parallel hybrid vehicle. So in series hybrid vehicle, you can see that it is like an electric vehicle. Electric vehicle, the propulsion is provided purely by the electric motor. In series hybrid vehicle also, the propulsion is provided purely by the electric motor. But the charging for an electric vehicle is done externally. Means you connect it to a wall plug and you charge it. But for the series hybrid vehicle, there is an engine in that vehicle. Engine drives a generator, and generator voltage is rectified and it charges the batteries. So whenever the state of charge of the battery falls below a certain level, then the engine turns on and charges the battery. Whereas in parallel hybrid vehicle, the propulsion is provided not only by the engine, but also by the electric motor. So both will act together. Parallelly, they provide the propulsion power. So that way the size of the motor can be less and the size of the engine can be also less. So smaller engine, smaller motor. Whereas in series hybrid vehicle, you can have a smaller engine, still you need a bigger motor, same as the size of the electric vehicle motor. So then there is a plug-in hybrid vehicle. So there is a electric vehicle, hybrid vehicle, and a plug-in hybrid vehicle. Plug-in hybrid vehicle is same as an hybrid vehicle, but you can charge the batteries externally. So for example, when you are parked or at your workplace or at home, you can charge the batteries. So that is similar to electric vehicle, you can charge it. So architecture is similar to hybrid vehicles, but charging is similar to electric vehicle, but the battery is a bigger size. So then what is the advantage of plug-in hybrid vehicle is, if you have a bigger battery, if you charge it overnight, you can drive certain miles pure electric. For example, Chevy Volt, I will talk about it soon. It was, now it is not sold anymore. It was giving 55 miles pure electric. So if somebody is driving less than 55 miles a day, and then in the night time they charge it, then this vehicle can be used only as a pure electric vehicle. They never have to fill up the gasoline for that vehicle. Only if they go for long distance, then the gasoline will be used. So that is the advantage of plug-in hybrid vehicle. So even in a hybrid vehicle, there are various categories like micro hybrid, mild hybrid, full hybrid. A micro hybrid is like an existing car, but in an existing car, there is an alternator. Alternator is used for what? Charging the 12 volts battery. So here, instead of using just as a generator to charge the 12 volts battery, what you do is you convert as a starter generator system. So you make that alternator also as a motor. Any electric machine can be made as it can be a motor or a generator. So instead of using as a generator only, you can make it as a motor also. So you need an inverter, a small inverter from 12 volts, and you can start the engine using that. You can start the engine. So when do you use that? Whenever the vehicle stops at signal lights, or when it is going down a hill, so you turn off the engine. So when you turn off the engine, so you save the fuel and also you lower the emissions. Okay. And mild hybrid is also similar to the micro hybrid, but the electric motor is in the same shaft of the engine and the transmission. So that way you can put a higher power motor. The higher power motor, if you use, you can get more power. And also when you pass another vehicle, then it will give extra power. And also when the vehicle is climbing the hills, it can provide extra power. Full hybrid is like a Toyota Prius, where the motor and the engine both will be working together to provide the propulsion. And that they are all parallel hybrid concepts. And regarding the this one series hybrid vehicle, as I said earlier, you see that propulsion is provided only by the electric motor. So there is an engine, a generator. So there are two types: a range extender vehicle or a full series hybrid vehicle. So range extender vehicle uses a smaller battery, smaller engine and a smaller generator and a bigger battery. So whenever the state of battery charge is low, then you turn on the engine, it drives the batteries. It drives the generator and charges the batteries. Whereas in a full series hybrid vehicle, the propulsion is provided by the battery and also by the engine driving the generator. So the power is directly going to the electric motor from the generator, and also power is going from the battery to the electric motor. Okay. So both will be acting together. You can replace what happened? You can replace the engine and the generator by a fuel cell, then it becomes a fuel cell vehicle. Okay. So if you see the degree of hybridization, micro hybrid has a 5 to 10% fuel economy, and mild hybrid 7 to 15%, full hybrid greater than 30%, plug-in hybrid can give greater than 15% in fuel economy. So power levels for the micro hybrid is 3 to 5 kilowatt, and for mild hybrid is 10 to 20 kilowatt, and for full hybrid it is greater than 20 kilowatts, and for plug-in hybrid it is more than 20 kilowatt power. Okay, that is the electric motor power. But the engine will also be there. In addition to this, there will be engine providing the power. And you see that micro hybrid, you can use it for automatically start-stop the engine. And mild hybrid, you can use it for regenerative braking. And also it provides the assist to the internal combustion engine. If you use a full hybrid, you can use it in an electric motor. For a plug-in hybrid vehicle, you can recharge the batteries from the outlet. So these are the advantages. So these micro and mild hybrids are getting very popular in Europe because by 2022, the next year, or by the end of this year, they want to bring down the emissions to 95 grams of carbon dioxide per kilometer. So that is their goal. Right now, it is more than 100. So what they want to do is, in addition to electric and hybrid vehicles, take the existing cars and make them convert by putting a small inverter as an integrated starter generator. There is the belt-driven starter generator, it is called. And so that way, you can save about 5 to 10% in fuel consumption and also reduce the emissions. And so that is the belt-driven starter generator system, and it operates at 48 volts. They want to increase the voltage to 48 volts. And the other one is the integrated starter generator. That is the mild hybrid. You see that this is the electric motor is mounted between the engine and the transmission here. So that way you can put a higher power motor. Here the motor power is about 2 to 3 kilowatts. Here you can go to 5 to 10 kilowatt motor can be used in this case, because the motor can transmit more power when it is on the shaft. Okay. So series hybrid vehicle, as I mentioned earlier, the engine drives the generator and there is a rectifier. The power goes to the electric motor directly, and also the battery power also can combine together. So both the power can be combined. So that is the series hybrid vehicle. So it is a simple drive systems, and the electric, the propulsion is purely electric. And whenever you want to charge the batteries, the engine is turned on and it drives the generator and it charges the batteries. So parallel hybrid vehicle, so the engine, the transmission, the power is going like this, and also the power is going like this. So it uses more than one energy converter can provide the propulsion. And also the motor can be smaller and also the engine can be smaller here. Or you can put a clutch here. So if you open the clutch, then the battery inverter, then it becomes a pure electric vehicle also. So that is also another possibility. So then there is a series parallel combination of hybrid electric vehicles. So you have a internal combustion engine can be driving the front wheels, and the electric motor can be driving the rear wheels. Here, the battery. Or the engine power is going directly to the wheels, and also engine drives a generator and charges the battery, and the battery power can go directly here. When a very high power is required, then the power goes like this, then the power goes like this, and power can go all the way down. So there are various possibilities in series parallel combination. For a Toyota Prius is a series parallel combination system. So this is the Toyota hybrid system. So that is where the power, this is a planetary gear system. The planetary gear system. So the engine power is combined. Then the engine drives the generator, and generator charges the batteries here like this. If there are two inverters here, even though it is shown as one inverter, there are two inverters, one for providing the, I will show you the diagram next slide, and the motor power, they are all combined into one here. Okay, and then it goes to the drive the wheels. This is the differential. So see, as I said earlier, so there is one inverter, it provides the propulsion power, and another one, this acts more like an active rectifier and charges the, provides the power from the generator, and Also, the power goes from here and the power also goes from here. When not much power is required by the electric motor, then it charges the batteries also. So that is the Toyota Prius, and Toyota uses this type of architecture in most of their hybrid vehicles. So Toyota, for example, this is how it is. They were earlier first generation. There was first generation 288 volts, but there was no boost converter. And battery voltage was 288 volts. That was going directly to the inverter, and the motor power was 33 kilowatt. Second generation, they used 202 volts with a 500 volts DC link voltage, 50 kilowatt. And the next generation, the battery is 202 volts. They increased the voltage to 650 volts using the boost converter. That way, the power went up to 60 kilowatts. So it gives about 38 kilometers per liter, so nearly 40 kilometers per liter. Hyundai also is a similar hybrid architecture. Hyundai used to have that mild hybrid architecture. That is the integrated starter generator, which I showed you earlier. But they discontinued that system. Now they have a system similar to Prius, but the operation is quite slightly different. They have a engine, they also have a generator, motor, 2 inverters, 2 motors, and they boost the voltage to 700 volts. The battery voltage is boosted to 700 volts. It is shown here. So at low speeds, it operates as a pure electric vehicle. At normal speeds, if the speed goes up, then the battery, it also acts as the electric power, and the power is also coming from the engine driving the generator. So the power is coming from both. At high speeds, generally only the engine is operated at high speeds. Okay, the battery and the motor will not be providing any power. But when more power is required at high speeds, then the battery and the motor will come into picture that adds the power to the engine power. So that is slightly different from the operation of the Prius. So plug-in hybrid vehicle, as I mentioned earlier, you use it as an electric vehicle as much as you can. Then once the state of charge of the battery falls below a certain level, then the engine is turned on, it drives the generator and charges the batteries. Then you maintain the state of charge of the battery by controlling the engine, by when the engine has to be turned on, when the engine has to be turned off. So you maintain the state of charge of the battery at a certain level. That is the plug-in hybrid. So Toyota Prius is a plug-in hybrid, or a Toyota. There is a Toyota is a plug-in hybrid vehicle. It is called Prius Prime. And Prius Prime. So it has an electric vehicle range of 25 miles, and with full charge of the batteries and full tank of the gasoline, you can go 640 miles, means almost 1,000 kilometers. So you can go 1,000 kilometers, maybe from Bangalore to Bombay. I think it's about 1,000 kilometers, right? So that much you can go without stopping the vehicle anywhere if you want to. So that is the advantage of the plug-in hybrid vehicles. Okay, and it uses 600 volts, battery voltage 351 volt, so it is boosted to 600 volts. Okay, and 2000 Chevy Volt, it is no longer available. They discontinued because of the expensive, and also people are not buying as many vehicles as they wanted to sell. But this was the best designed plug-in hybrid vehicle. This was the first plug-in hybrid vehicle that came into market, and a lot of people bought it. So it has a pure electric vehicle range of 53 miles and was giving equivalent to 106 miles per gallon. That is nearly 170 kilometers per 170 kilometers per gallon. That is quite a good one. And overall range is 420 miles. That is with full tank of gasoline and fully charged batteries. But it is not available. So they had two motors, and they had one is a 87 kilowatt permanent magnet motor, neodymium iron boron, and 48 kilowatt, the smaller one, which acts as a generator, mostly is the ferrite motor. It was a ferrite motor, not a permanent magnet motor. So so that way they could reduce the cost of the overall motor there. Then fuel cell vehicles. I think most of you know how a fuel cell works. The fuel cell, as I will give very briefly tell you how the fuel cell works. So there is an anode and a cathode. So fuel cell works. There are different types of fuel cell, but we will talk only mainly about the PEM fuel cell. PEM is proton exchange membrane fuel cell or polymer electrolyte membrane fuel cell. It operates between 80 to 100 degrees Celsius. Okay. So generally, all the fuel cells, like solid oxide fuel cell or any other fuel cell, they need hydrogen as the input. Hydrogen is the fuel. So in the case of PEM fuel cell, if you supply hydrogen, and then you have to also supply the oxygen at the cathode. Okay. This is the anode and this is the cathode. And this is the electrolyte material. Then, so supplying hydrogen at 80 to 100 degrees Celsius at the anode, there is a platinum catalyst. With the help of the platinum catalyst, hydrogen dissociates into hydrogen ion and electron. So 2H plus and 2E, it becomes at 80 to 100 degrees Celsius. That is where the fuel cell operates. And with the help of the catalyst, platinum catalyst. So there is a electrolyte material that is a proton exchange membrane material that is selected in such a way that allows only the hydrogen ions to flow through it, not the electrons. So the hydrogen ions will flow through the electrolyte material and reaches the cathode. This 2H plus will come to this side, and the electrons have to go through the external circuit. You connect some electrical load, so it flows through the external circuit and reaches also the cathode. At the cathode, this hydrogen ions are called the protons, combine with the electrons, and oxygen is also supplied at the anode. It is supplied in terms of air, then it is filtered out and it becomes oxygen. It combines with the oxygen and produces water. So in the fuel cell, what do you produce is water and the electricity. Electricity came like this and you produce the water. So the fuel cell operates by supplying hydrogen at the anode and oxygen at the cathode at 80 to 100 degrees Celsius. Using the platinum catalyst and the proton exchange membrane, you can produce electricity and water. So we will let go the water and we can use the electricity. But each fuel cell only provides 1 volt. So we connect number of cells in series to get higher voltage. So if you need 100 volts, you need to connect 100 cells in series. So, but as a fuel cell operates around 0.7 volts when it is loaded. So if you really need 100 volts when it is loaded, then you need 144 cells because each cell operates at 0.7 volts only. Okay, that's how. So you can have, so now you have a fuel cell array stack, it is called. Number of cells are connected in series and parallel, that is called a fuel cell stack. That provides DC and its voltage changes depending on the load. That's why you need a DC-DC converter, and also, of course, DC to AC, you convert it. And how do you get the hydrogen? Hydrogen you can obtain using electrolysis of water or reforming gasoline or methanol or ethanol and all those things. Reforming means converting any fuel to hydrogen is called the reforming process, and it is called the reformer. Okay, and also you can use an additional battery to provide the power during the transients. So that is the auto fuel cell system. Yeah. Why it is not moving? Okay, so your fuel cell unit, and it is a battery. You have a DC-DC converter to match this voltage to battery voltage, to the inverter voltage to the battery voltage. And this is the propulsion inverter and a motor, and motor will have a closed loop controller. In addition, you need to have a propulsion system controller. So it controls the power demand, and a hydrogen to the fuel cell has to be controlled. How do you control the hydrogen to the fuel cell? It depends on the amount of current required. Hydrogen is current. So you need to measure the current here. The current has to be controlled by controlling the, depending on how much current you need, that is coming from the propulsion system controller, this reference, and compare the fuel cell current and then adjust the hydrogen input. So hydrogen input is adjusted or varied according to the required current. And there is a diode here because we don't want the current to the flow, to negative current to flow to the fuel cell unit. That's why we always use a diode series. So this is the 2015 Toyota Mirai. I had another slide showing 2021, but more or less similar. Slightly, the price has come down to 49,500, and now it can take 5.6 kilograms of hydrogen at 70 MPa. More or less similar architecture. Okay. So 1 kilogram of hydrogen, 1 kg of hydrogen, and 1 gallon of hydrogen, 1 gallon of gasoline, they have the same energy density. Okay, 1 kilogram of hydrogen has the same energy density as 1 gallon of gasoline. So when you use in a car, when a fuel cell car, if you use 5 kilograms of hydrogen, it is equivalent to using 10 gallons of, equivalent to using 10 gallons of gasoline energy wise. And also, I mean 5 gallons of gasoline, but equivalent to 10 gallons because the fuel cell, the system is twice efficient than the internal combustion engine based system because of the electrical systems are more efficient. So this is the Toyota fuel cell system. Maximum speed is 110 miles power, and you can go 404 miles range. Okay, and normal operating pressure is 70 megapascals. So charging, there are two types of charging, basically conductive charging and inductive charging. Conductive charging, you have a AC to DC, and then you charge the batteries, you control the DC and charge the batteries. Whereas inductive charging, you have to drive, there is a pad here, you can see here. And so you drive the vehicle there. The primary of the transformer, I will show you later, is buried here, but the secondary is in the car. So you just have to drive the car up to a certain point, and automatically it charges the batteries. And there is a fast charging. So fast charging enables a direct connection to the DC loads. Direct DC loads to the vehicle battery for the very fast rate charging. Direct current charging. So there are super fast charging stations are available now. So you can charge, for example, in 15 minutes of charging, you can go up to 500 kilometers. Super charging stations. Super fast charging stations at various places in the country. And there are Siemens is producing For example, 150 kilowatt at 920 volts. Recently, BYD of China, they got a UL approval for 150 kilowatt fast charger from UL, that underwriting labs. So there are several companies are working on fast chargers now. The idea is to install these fast charging stations all over the country. Like we have a gas stations all over the country. Anywhere you can go and fill up your gasoline. Like that, you can go anywhere you go and charge the batteries. So this is the conductive charging, electrical load, AC to DC converter, and there is the DC-DC converter and charges the batteries. Recently, there is more and more bidirectional converters are there. Instead of unidirectional, you make them bidirectional so that you can have a power going to the grid also. So when the electric vehicle most of the time is not being driven, so at that time you can connect it to the grid and provide the power. There are various topologies, I think, for DC-DC converters and for charging and all those things. I think I will skip that one. And a wireless system, as I mentioned earlier. So you have a three-phase power, and then you have a primary here, and this is the pickup inductance. This is in the vehicle, this portion, and this portion is in the ground. So you have to drive up to a certain point, and it charges the batteries here. So this is the block diagram of the wireless charging system. AC, rectifier and filter, inverter, high frequency, and this is on the ground, wireless, and this is in the vehicle, battery. So recently there is a lot of interest in using wide bandgap semiconductors in electric vehicles because they can operate at a very high temperature of the order of theoretically up to 300 degrees Celsius. The reason they want to go for a higher temperature devices is then you can have a smaller heat sink, so you can reduce the size of the overall inverter. For example, this is a silicon device and this is silicon carbide. So the Toyota has recently tested, they say that they can reduce it by 1/3 using silicon carbide devices. Also, silicon carbide devices are higher bandgap voltage, and so they have a better thermal conductivity than the silicon devices. A recent trend is to integrate the motor and inverter. So there are several companies like Borg-Warner. Borg-Warner is one of the major suppliers of drive systems for the electric vehicles. They do it for many companies. So you basically connect the battery terminals here. The inverter and the motor, they are all inside. So, and this is another design. So what are the trends for the future? The Department of Energy has commissioned this electrical and electronics technical team roadmap. So their requirement to advance the technology so that you can reduce the cost and increase the power density. So these are the technical targets. Power density, they want 50 kilowatt per liter by 2025. And for that is for the electric motor, and for the power electronics, cost has to be $2.7 per kilowatt, and power density 100 kilowatt per liter, and even for DC-DC converter. These are all the technical targets. So where are we going next? So we started with 12 volts start-stop. That is the micro hybrids, then 48 volts integrated starter generators, then full hybrids like Toyota Prius, plug-in hybrids like Toyota Prius Prime, electric vehicle like Tesla. Now there is a lot of work going on connected electric vehicles. That is self-driven, connected, autonomous, self-driven, autonomous cars. Basically, they are self-driven, and connected electric vehicles, and also vehicle to grid operation. In connected vehicles, the vehicles can talk to each other and communicate. That is the one. So the power electronics is a very important technology. So whether it is for the airplanes, for the cars or anything, you need the power electronics. Without power electronics, we cannot do anything. Not only for transportation, you need power electronics for everything. So if General Motors by 2035 wants to go for pure electric vehicles, an electric vehicle is nothing but electric motor and power electronics. How many electrical engineers they need? Right now, they employ so many mechanical engineers for this internal combustion engine systems. But so now all those engineers will be replaced. So if so many auto companies in the world, they are switching over to electric vehicles, there will be a large shortage of electrical engineers that is required. For example, Norway wants to replace everything by 2030. I think all vehicles have to be electric vehicles. So the trend is towards electric vehicles. So I think, yeah, I will stop here. Maybe I can answer more questions if you have. Okay. Because I think we exceeded our time. I think so.
Yeah.
Because we didn't start it late anyway. So, any questions you have?
So thank you very much for your wonderful talk, and we're fortunate to have you today, sir. And now I request the participant, if you have any questions, please unmute yourself and then interact with the speaker.
Sir, good evening, sir.
Good evening.
Sir, on permanent magnet synchronous motor, may I know the research focus point currently the industry is looking at?
The permanent magnet motors, they are using neodymium iron boron magnets. So those magnets are quite expensive. So people are working, or many automotive companies are also working on how to reduce the amount of magnet that is required. Because it is quite expensive. Like General Motors, they try to even eliminate, but they could not do it for the big motors. Small one using, they replace with ferrites. But ferrites, it's difficult to use for propulsion, then it becomes bigger one. So there is a lot of work in reducing the amount of magnet that is required in using the permanent magnet motors. Another one, the synchronous reluctance motors. So synchronous reluctance motors are also being considered, but they don't need any magnet. They run at synchronous speed, but their power factor is poor. So people are also looking at PM assisted synchronous reluctance motors. So synchronous reluctance motors or PM synchronous reluctance motors, a lot of work is being done in this area.
Thank you.
Okay, can I ask? Hello.
Yeah.
Yes, sir. Please.
Rajashekara.
Yeah, Murthy, yes. Go ahead.
No, actually, you see, there are some questions are being asked every time. See, we have to charge the batteries for charging, and then one of the objective of this whole thing is to reduce emissions. Okay.
Yeah.
But the question they say is, for charging you need electricity. To produce that electricity, that will produce emissions. Okay.
Yeah.
That is one question that people will ask. That is my question number one. Question number two is, battery, you say lithium ion is the in thing now. It appears, and I think that also appears to be China dependent. Is one thing. Third is permanent magnet motors. Of course, are already they are the prime motors nowadays, as you said, in the vehicles. But again, there is also China dependent permanent magnets. Okay, and therefore, as you said, that the synchronous reluctance motors may be a better option. And perhaps induction motors may be giving way to these type of motors. I just wanted your reaction to some of these issues.
Yeah, good questions. Let us start from the third one because we are talking about the motors. I like induction motor, whatever you said, because
Same
in
with me.
general motors we were using induction motors to start with. Only thing is a slightly lower efficiency than permanent magnet motors, but they are so rugged and they are not like in the permanent magnet motors. The problem is the fault tolerant. In induction machines, we don't have that problem, and also they can also operate at a higher temperature than permanent magnet motors. So there are a lot of advantages. Even for airplanes, I published several papers on induction generators. They use synchronous motors now. So I was pushing for induction generators rather than synchronous generators. I think that is good. And if not, even synchronous reluctance motors with the PMS assist, that doesn't need a lot of permanent magnets. That would be a better option. I think they are correct. And regarding the charging, charging, it needs electricity. But the trend is to go for renewable energy. Now, more and more countries are producing a lot of, by 2030, for example, California is selling 50% of their energy has to come from the renewable energy sources. And also Denmark, more than 50% is coming from renewable energy sources. So if the electricity is coming from renewable energy sources and charge the batteries, then it's okay. Then there are no emissions. But there are also coal plants are being used. So coal produces 1100 grams of carbon dioxide per kilowatt hour. But even with that one, it is not bad because those power plants are in rural areas, very far from the urban areas. So it reduces the urban pollution. But right now in the United States, at least I can tell, more and more coal-based plants are replaced by natural gas plants. So oil-based plants, there are hardly any oil-fired plants, but coal are being replaced. Coal is coming down. I think 2040, I think the coal plants may go down may disappear or they may completely go down. So natural gas is not bad. Natural gas is 600 grams of carbon dioxide per kilowatt hour. So it is almost off. But over the years with renewable energy, I think we should be okay. Your middle question was related to the batteries. Yeah, right now lithium-ion batteries. A lot of the China makes the lithium-ion batteries, but there are other companies also. Australia has a lot of lithium resources, and also there are some African countries are there. So the problem with the people ask is the question is not so much on the China with respect to the batteries, but what do you do with all those batteries after using? Because that create the emissions, because so many cars are there with lithium-ion batteries after some time. So what is being done is to extend their life. You use those used lithium-ion batteries in the cars as grid energy storage elements. So for example, Toyota has been using nickel metal hydride batteries in their vehicles, and Prius still uses the old Prius. They use still nickel metal hydride batteries. So once after a certain year, say after 8 years, they will take it out and give it to other companies. They make it big megawatts of energy storage units. So because for energy storage, you don't need to discharge so much. Only the state of charge can be maintained at a certain very narrow level. So then it is fine. So that way it is further extended. So in a long run, we have to see how, fortunately, we don't have so many electric vehicles on the road now, but we have to see how it is going to evolve. But there are other types of battery technologies are also coming up. Maybe we will have some other solution.
Okay, I have just one more question.
Okay.
See, I'm just looking for an Indian scenario, which you also know. Here, our emphasis should be not the four-wheeler cars, but two-wheeler scooters, then three-wheeler auto rickshaws or whatever, then mini buses, and these are the priorities in India. Number one. Now, obviously, we may have to reorient our designs, etc., to these type of new vehicles. We should run on batteries. And next is our roads are very bad.
Yeah.
Now,
That's correct.
now that is again another hiccup in using electric vehicles. So I just, since you know the local Indian conditions, you can react.
Only in the highways it is good, but the local roads, Professor U.R. Rao, the space ISRO chairman, he is no more now. When I was a student at Indian Science, he visited. I was a faculty or a student. He told me that he doesn't have to test the satellites, especially in India, because once he takes these satellites on the road, they are all very well tested for vibrations. That's what he said. So vibration done is by testing on the Indian roads. That's all. Test to be done. So like that. But I think the roads are getting better, because once the roads are not good, the range also will go down, because the vehicle goes up and down and all those things. That is a problem. But highways are these days okay. And regarding the three-wheeler and two-wheeler, I think rickshaw is the most commonly used vehicle. I think that should be made electric vehicle. Scooters, I think should go away over the long run, because they are very unsafe. That is what I feel. For local, okay, but not for long distances and other scooters. I don't know. Yeah. But anyway, they have to be converted to electric. There is a lot of work done on converting scooters to electric. Many are producing already electric scooters. In Taiwan, for example, they have a lot of electric scooters.
Yeah, but I think mini buses are very useful in India.
That's correct. Yeah, mini buses also. That's correct.
Yeah,
mini buses.
Yeah. Sir, there are two questions in the chat box. With your permission, I will read it. Yeah, the first one from Mr. Baumik. The question is, what is the preferred switching frequency range for EV inverter? And is there any reason for choosing that range?
Yeah. General, see, we don't want it to be audible. The human ear is sensitive if it is less than 20 kilohertz. So we switch more than 20 kilohertz, but you have to see that the switching frequency increases, switching losses increases. So if you are using IGBT, so we started switching the devices when we were working for the electric vehicles at 20 kilohertz. But our losses were high. We finally made it to 12 or 15 kilohertz, but it was not that bad. But with silicon carbide devices, you can switch at higher frequency. 50 kilohertz is you don't find any problem switching the silicon carbide at 50 kilohertz. There won't be any switching loss problems. So it depends on the type of device you use for that type of applications. So if it is a MOSFET, 20-25 kilohertz is fine, but if it is IGBT, it has to be maybe less than 20 kilohertz.
Okay. Next one, sir. What is the preferred power factor correction topology?
For charging? For charging?
Yes.
For charging,
yes.
Yeah, active power factor, active rectifier.
Yes.
Active rectifier is the most commonly used one.
Okay.
You can get almost unity power factor.
And one more question, sir. How do you like to compare 48 and 72 voltage EV charging as in India with reference to higher battery voltages in abroad? Which is the advantages if you are considering for the fast charging?
So this 48 volts, the idea for 48 volts is different than what is the 72 volts? I don't know where in India you use 72 volts. I didn't know about that. 48 volts in Europe is not for electric vehicles. It is for this micro hybrid or mild hybrid for the where the electric motor is a very small motor, less than 10 kilowatt, or even sometimes if it is belt driven, it is only 3 to 5 kilowatt. So if you go for more than 48 volts, 72 volts, 72 volts may be okay for a auto rickshaw, but not for a car, because car needs, it depends, at least peak power of 100 kilowatt or maybe 75 to 100 kilowatt, even a four passenger car. 72 volts will be very low, then your current will be very high, then the power losses will be very high. So generally that low voltage 72 volts for a pure electric vehicle is not a suggested voltage. For example, Tesla and General Motors cars operate 300 to 400 volts. The trend is to go for a higher voltage, 700 volts, like that, the trend. So the current is low, so you can go for a higher power.
Okay. Yeah. If any questions, please participant. If no questions, we'll conclude the session. Yeah, one more is added. Are the super capacitors are using any of the cars?
Yeah, some cars they use, Honda uses in some cars. There is only, particularly in the hybrid vehicles, advantage of super capacitors are they have a high power capability, but low energy density. Energy density of super capacitors are very low, 10 watt hours, 15 watt hours, like that. But they have high powers. For example, when you want to suddenly accelerate or pass a vehicle, then we need more power. So that can come from the super capacitors, and you can use them. There are few cars, but not many.
Okay. Yeah. So last question, sir. What is the overall efficiency of hydrogen-based car?
That fuel cell car, I would say, is about 2 times the efficiency of internal combustion engine. About internal combustion engine based vehicles are about 15 to 20%. The fuel cell vehicle car is about 30 to 35%, around 32%, and internal combustion engine is about 15 to 20%, I would say, or even less than 20%.
Okay.
Overall efficiency, well to wheel.
Yeah.
Oh, well to not. Yeah, well to wheel. There are 2 types of well to tank and tank to wheel. So this is well to wheel efficiency.
Yeah. Thank you, sir. I think we're ended the questions also. Yeah.
Okay, thank you for the invitation.
Yeah.
Thanks all of you.
Yes. Yes.
So thank you, Murthy. We will talk later sometime.
Yes. Yeah. So let me give the formal vote of thanks for this session, sir. On behalf of IEEE Vizag based section and IEEE Power Electronics Industry Applications and Power and Energy Joint Society chapter, so I would like to thank Professor Kaushik Rajashekara from University of Houston, USA, for delivering this IEEE fellow talk on this evening today. So thank you very much, sir, for your kind acceptance and deliver the first fellow talk for our section. Actually, we will continue these fellow talks every month, and we will share the knowledge with our all participants and fellow members also in this section. I would like to thank Professor S.S. Murthy for joining as a panelist member in this event. I would like to thank also Dr. Lakshmi Narayana, Chair Vizag Bay section, and I would like to thank the section EXCOM members and chapter EXCOM members and my dear participants who have attended this program and then made this event as a grand success. Thank you everyone, one and all. Thank you. Thank you so much.
All right,
And,
thank you all of you, and
yes.
nice meeting you in synchronously online.
Yes.
Hopefully we can meet in person one day in the future.
Yes, sir. Sure, sir. And we would like to invite you in the next year. So once the pandemic is over, and we are I'm happy to invite you to the India and then our institute as well as IEEE section, sir. Thank you so much.
Thank you.
Yeah.
Bye.
Yeah. So next fellow talk is also scheduled, sir, actually. So it is on February 28th by Professor Prasad NJT. Sunday we have scheduled it. So we are in advance to that also. And also, apart from fellow talks, we are also arranging some expert lectures by different industry engineers also, so that we will, continue our activities and share our knowledge to all the professional members as well as students and faculty in our section. So thank you. Yeah.
Yeah. Thanks. Bye.
Thank you, sir. Thank you so much, sir.